Hello. Welcome to Team 8's senior project, an electron tunneling microscope. This project was sponsored by Grand Valley's Physics Department and Dr. Joshua Veazey. The faculty advisor for this project is Dr. Carl Bracora. The members of this team include Nathan Koch, Dustin Matthews, Sean Folo, Jacob Kaczynski, Kelsey Marquez, and Megan Sikora. Professors in Grand Valley State University's Physics Department first introduced a novel design for a single-axis electron tunneling microscope in 2022. Following a further design iteration, the GVSU Dewar Center produced several functioning prototypes that have been used in the laboratory by advanced undergraduate physics students. The GVSU Dewar Center, in cooperation with the Physics Department, has sponsored a senior design project to revise an electron tunneling microscope with the intent to 1. Improve the speed of data acquisition. 2. Reduce the cost per unit. 3. Reduce the setup time. What is an electron tunneling microscope? It is a simplified, single-axis instrument. The device allows the students to measure surface energy states of different materials. It requires extremely small-scale distances and currents in order to function properly. In order to use the electron tunneling microscope, first, it must be set up by placing the tip and sample and making connections. Then, coarse and fine adjustments are performed. Finally, the user must interact with the GUI to control the microscope and collect data. These are the key specifications for this project. Some of these include: the total cost of all 5 devices must be less than or equal to $5,000. The tip must be capable of moving in delta Z steps less than or equal to 0.10 nanometers. The device must use a distance control algorithm to control the tip's approach to the sample. The GUI must display currents, voltages, and approach distances. There were some major obstacles for this electron tunneling microscope that were faced throughout both the design, building, and testing stages. The first obstacles is refining the tip approach algorithm. The next major obstacle was making the tip assembly as simple as possible to build and to replace the tip when necessary. Another major obstacle was achieving levels of precision necessary to be able to detect both nanoamps and picoamps of current. The last major obstacle was the design of the DAC circuitry to achieve the level of precision that is necessary for all of the control signals. This is the 3D design for the electron tunneling microscope. This includes the 2 coarse adjust micrometer screws that will be operated by the user to get the tip within 1 mm of the sample. The fine adjust screw will be controlled by the stepper motor in small steps in order to reach the tunneling current of the sample. The stepper motor slide holds the stepper motor mount and allows the stepper motor to move up and down vertically. The top plate also holds the preamp board, which contains the transimpedance amplifier, which has a very high gain and converts the current to voltage. The preamp board also includes the differential driver that conditions the signal for the ADC. The bottom plate holds the sample board PCB and also includes grooves for the micrometer screws to rest in. Inserts were added into the top plate for the micrometer screws due to their extremely fine, uncommon threads. In order to eliminate noise while collecting data, an enclosure is used to house the electron tunneling microscope. In order to connect the internal components to the outside electronics, a connect bracket was designed to hold connectors, while also still ensuring the internal components are shielded. Another small enclosure was also modified for the control board and power board, in order for the different connectors and switches to be accessed. Here is the physical machined and assembled electron tunneling microscope. A border was added to help align the enclosure lid when being placed over the microscope. Coarse and fine adjustment screws are used to move the tip closer to the sample. The fine adjust screw is controlled by the stepper motor and data is sent to the GUI to show when the tip is measuring the tunneling current of the sample. These are the graphical user interfaces that will be used to collect data and interact with the electron tunneling microscope. The home screen is used to seek tunneling current based on the user inputs and then display the periodic data onto the graph. The user is able to finely adjust the tip and adjust the stepper motor. The user is also able to reset the tip home position and save data with the drop-down menu. The IZ window is used to determine current as a function of piezo voltage. The user is able to input a minimum and maximum voltage value that the microscope will then use to sweep through and collect data. The IV window functions the same way, but it is instead a function of the sample bias voltage versus current. In order to build this electron tunneling microscope, the components were all machined in different ways. The top and bottom plates are made of aluminum. They were first cut to size and squared. Once the 3D model of both plates were created in SolidWorks, Both plates were then cut using the Haas CNC machine. Both the connector bracket for the large enclosure and the plates on both sides of the small enclosure were cut out using the Lincoln Electric Torchmate 4400, which is a CNC plasma cutter. In order to achieve the correct dimensions for all of the cuts, all components were first modeled in SolidWorks. For the connector bracket, once cut, the bracket was bent at a 90-degree angle so that it could sit under the enclosure lid while also laying flat against the enclosure to ensure shielding. All components were smoothed and polished to ensure a clean and smooth surface finish. The stepper motor slide was 3D printed using stereolithography. This type of 3D printing has high precision and a smooth surface finish, allowing for the stepper motor to move up and down smoothly within the slide. A large design change that was made was the tip design and assembly. The old tip was difficult to assemble and hard to hold all the components together while using the epoxy. The new tip includes a 3D printed component to make the placement of the piezo with the epoxy easier. The new design also includes a spring mechanism and a washer to help ease the insertion of the wire into the tip. The new design overall allows for easier assembly compared to the old design. It also allows for a faster changing of the platinum iridium wire. In order for the boards to be usable, different components must be attached to the boards. Here solder paste is being applied to the pads on the PCB using a stencil. After the paste is applied, the components are then placed onto the PCB. Then, the boards are put into the oven, which melts the solder paste and permanently attaches all of the components. Here, hand soldering is being done to put components onto the power board. Here is the stepper motor taking steps to adjust the fine adjustment screw for the tip approach. you for watching our video about our electron tunneling microscope for 2024 senior project.